Hello, we are Group 5. We did the Home Automation and Power Monitoring Unit. My name is Hillary Neff.
I'm Meredith Godar.
And I'm Jared Corso.
So for our overall system, it's designed to be a system that can turn on and off an appliance in your home remotely. So we have two devices. One is able to turn a device on and off, and the other is able to turn the device on and off and read the power consumption of the device. And then those devices are interfaced over Wi-Fi with a server. And then we also have implemented an Android application that allows you to control those devices from your phone and also read the power consumption and view graphs of that data.
We broke this project up into 3 parts. I was in charge of the hardware.
I was in charge of the microcontroller firmware.
And I wrote the Android application.
So delving into the hardware side, a little bit of information regarding some of the design requirements. It had to switch large voltages and currents since you're plugging it in directly to the wall outlet. So we're talking 120 volts alternating current, as well as around 15 amps is what the typical draw would be in a household. We wanted to measure the average power, not the true or apparent power. So that means that you can't connect this device to any inductive load, because that would mean that you would have to use special power calculations, which this device did not implement. It had to have surge protection, as well as monitor appliances from 0 to 1,000 watts, plus or minus 5%. So we wanted it to be fairly accurate. And physically, we wanted to be the size of a laptop charger. And I don't know if you want to show it now.
We did do that part there.
So that's the device that is just the switch to turn the appliance on and off. And then we also have the device that includes the power monitoring.
Alright. So this is the schematic of the power monitoring device. If you want to take a look at the non-power monitoring one, you would just remove these 2 circuits from it. As you can see, we have 2 15 amp fuses before and after the surge protector, which would protect anything from power surge due to a thunderstorm or something that happened to the device that you plugged it into. Here you can see the relay that we used, and that is controlled by the electric imp, the microcontroller. Over here, sorry. Over here, I've written that the imp is powered by a 120 to 12 VDC switching power supply, and that also provides the voltage to turn on the relay. It's not shown in the schematic though. Actually, okay, this is fine. So measuring the power, power equals current times volts. So to measure it, we had to measure the current draw that the appliance was using, as well as the voltage of what was being used. So to do that, we used a current transformer, we used a current transformer along with a burden resistor and a bias network. And if you could go back to the other slide. This would be the current monitoring circuit. So you can see our current transformer, the burden resistor, which means we needed this because the current transformer would just transform the current being drawn into something a lot smaller. And to generate the voltage that the imp could read, we had to put this in here to generate the voltage. This is the biasing network, so that since this is a pretty small voltage, we wanted the imp to be able to read it, so we added a couple volts to it. To measure voltage, our initial design was to use an isolation amplifier, but right before we checked off, we burnt that out. So we quickly switched our design to using a voltage divider plus a bias network, which worked, but it wasn't as accurate as the isolation amplifier. So going forward, obviously, we would have this back in our design, but since time ran out, we had to switch to this guy. So go forward. That one. This guy. So here is the voltage divider circuit. We've got a very large resistor here to protect the in from any large input voltages. And again, you see the bias network to in this case, the bias network not only increases the small voltages read, but shifts it so that you don't have any negative voltages going into the amp. You can go ahead. Something that we wanted to do but didn't get a chance to procure was a PCB board. Before we put the product in the final packaging, we built this PCB schematic and found out afterward that it would cost $200 to build using this advanced circuits company. So in the end, we did not have $200 to spend on the PCB board. But if, as our customer, you would like this in your product, we have the schematic ready to go. And of course, for an additional charge of $200, you can have a PCB board instead, and it will definitely reduce the size of the product.
So on the microprocessor side, we looked at a couple different options, including using like an Arduino with Wi-Fi. We also looked at like the Zigbee, and then we ended up going with the microcontroller called the Electric Imp. It ended up being the cheapest option for us. So the Electric Imp is an ARM-based microprocessor. It has an internal Wi-Fi antenna, so it's nice. It's got a nice small footprint. And it's packaged inside of an SD card package, so it's really small. And then using this breakout board that we purchased from Spark, that's how we were able to connect our imp up to our circuit. And one unique thing about the imp is that each imp itself has an ID, but the actual ID that the code is tied to is from an Atmel authentication chip that is on the breakout board. So what that means for us is that if you burn out the imp or something happens to it, you can plug a new imp in that's hooked up to that Wi-Fi network, and it will automatically connect to the server and re-download the code, which we ended up using. At one point we burned out one of our imps, so when the new one arrived, we were able to just hook it up to the Wi-Fi, plug it in, and then with no extra steps it downloaded the code for us, which is a really handy feature. And the Electric Imp is programmed using Squirrel, which is an object-oriented language that's syntactically very similar to C. All of the code for the imp is based in the cloud. So when you initially get your imp, there's a photo transistor on the bottom here, and you hold that up to the screen on your smartphone, and in a process that they call blinking up, it programs the imp for your Wi-Fi network through your smartphone. And so once that's completed, you never have to actually connect the imp to a computer or anything like that to download the code. The code is always sent to the imp over Wi-Fi. So both the client, or as they call it, the device, and the server or the agent code is all stored in their cloud. For the agent itself, it consists mostly of an HTTP handler to process the requests from the application. So every time the Android application makes a request to turn the power on, turn it off, get the power readings, things like that, those are sent as an HTTP request to our server. And then the HTTP handler processes those and then makes additional calls to the device as needed to perform those functions. Power readings that we collect are then saved to the server so that those will persist over power cycles. So that if you lose power, you'll still have all of the data that you've collected previously, up to a week's worth of data saved on the server. And then additionally, the agent saves the device state. So if there is a power failure, when the power comes back on, whatever appliance you had hooked up to the imp will then go to the same state it was before the power failure. So either on or off, based on what was saved to the server. For the device, we've got functions that handle toggling the state of the appliance, sending the device state to the application so the device can check if the appliance is on or off, controlling the sleep and wake functions. So from the phone, you can set you want this appliance to turn on at 8 a.m. and off at 8 p.m. And then that will get implemented with the imp. And then we also have the power monitoring and sending the power data to the server. For the power monitor, we're using the sampler on the imp, which is a nice feature that lets you make calls to the analog to digital converter at a specific frequency. Or well, it actually doesn't, it reads the pins at a specific frequency, and then you can process the data and convert that so that you can get a lot of readings and you'll know exactly what frequency those readings are occurring at. So we were sampling 2 pins, one for voltage and one for current at 3 kilohertz, which allows us to get 100 voltage and 100 current samples over 2 full AC cycles so that we can get a nice picture of the waveform and make sure we're getting enough data to get an accurate power reading. The current conversion and scaling is based off of the specifications from our current transformer. And so our current factor ended up being 13.3. And the voltage conversion is based off of our voltage divider. And so that ended up giving us this number here that we use to complete the power calculations.
All right, so I'm going to give you an overall view of all of the screens, or most of the screens associated with the app. And then at the end, I'll explain the hierarchy of the code and how the things actually work. So the first screen you see when you open up the application is this login screen. And so the login screen has a field that prompts you for a username and password and lets you submit. With our device, the username and password comes with the device in the documentation so that it's unique only to you. But obviously in future versions, we would consider being able to create accounts, support multiple users, and some of those more advanced features. So the next screen after you log into the application is a selection of which device you want to control. So one of the devices, the defaults are just device 1 and device 2. And so one of them controls only the switching device, and the other one is the switching and power monitoring device. The name titles are changeable, and in the next screen, you can actually click on the device name, change them, and then those changes will persist throughout the entire application. And so there are 2 different versions of the device control screen. The one that's only for the switching on and off, and that's the screen on the left. And the screen on the right is the one that does all the extra features with the power. And so as you can see, there's a get status button, so you can check to make sure that our actual device is online and operating correctly. And then you just have the simple on and off, and then the set on and off time screen, which just takes you to another screen where you can set on and off times. And then, back one more.
Sorry.
And then the other version of the screen adds these additional fields that I have graph power, a field next to power, and then a reset button. The power button just gives you an instantaneous reading of the power usage. So you could at any moment say, give me the power, and it'll tell you how much power your device is consuming at that time. And then the graph button brings you to a graph of the last 2 weeks worth of power data, and the reset button resets that power data. So say you plug it into a new device and you don't want to see that old power data, you can reset it. So then the power graph has a couple pretty cool features. It dynamically adjusts the time scale on the graph. So if you plug it in and only have a couple hours or a couple days worth of data, it doesn't show you this graph with just data at the beginning and then a whole bunch of blank space at the end. And then in addition to that, it's got zoom and fit tools, as you can see in the bottom right hand corner, so you can zoom in and out. And then there's a button to snap it back to a 1-to-1 ratio of the graph. And in addition to that, you can also touch interact with it, so you can drag your finger along and scroll the graph to different places, and you can also pinch zoom on the graph to zoom in also. So there's kind of this hierarchy that goes along with Android application software. So every screen corresponds to an activity, as it's called in the Android Java lingo. And each activity comprises of an XML layout and then a Java class that has all of the functions to run that screen. And so as you can see, and as we kind of went through it, there's this hierarchy. You log in and then go to device selection, and then device control, and then on to power. And then when you actually go to a new screen, it doesn't actually kill the process that was running prior. It kind of hibernates it. So like if you hit the back button and go to the previous screen, it just pops that back open and doesn't have to repopulate all that data. It's still held in memory. And then there are a couple extra classes that handle some of the utility stuff, most specifically the networking class, which I wrote. It asynchronously makes HTTP calls, so it uses the built-in HTTP client to make the calls, but then runs it in a background thread so you don't load the main thread or slow down, visual operations. And then it has handlers for whether the call was a success or was a fail, and then the app, reacts correspondingly. And then all the graphing was done with a library, and then some modifications done to the library to make it fit for our application. And so that brings it to you guys. You guys have any questions?